Free body diagrams. The free body diagram, or FBD, is a cartoon tool which is used in dynamics to help illustrate a situation. The basic idea is this: for every object of interest, draw the forces acting on that object with correct directions and ideally correct magnitudes. Then you can use a diagram to construct equations using Newton's second law to relate accelerations and forces. One of the key things is that you're drawing the forces on the object. That's why it's free. It's not in contact with or connected to anything else. So if you have two things that are connected by a rope, the rope does not appear. It only appears in the tensions that it's exerting, not as a thing itself. And if the objects are touching, then you use their normal forces between them to represent the contact. You don't draw them in contact. Example: Alice rides a rocket directed entirely vertically. The rocket pushes against her with a force which is given as Fr equals 1100 newtons, and the Earth also pulls on Alice with a force which is given as Fg is 540 newtons. Alice's mass is 55 kilograms. Draw a free body diagram for this situation. Of course, we'll know a little bit later that the weight, it's not an accident that her mass is 55 and her weight is 540, but for now just take them as given. So we draw a diagram for Alice. Take a second to sketch that and come back. Notice we're drawing a free body diagram, not a picture of the motion. So here is Alice, looking maybe a little aggrieved. And Alice has a rocket pushing up against her with F sub r, and she has gravity pulling down, F sub g, and here I've just drawn that they're not equal to show that the rocket is pushing her, managing to push her upward. It would be semi-traditional, but not at all necessary, to also put that we know she accelerates upward. But the acceleration is not part of the free body diagram. It's sort of just a note for our own later use and should never be attached to the object the way the forces are. Also, the AP committee has moved to this new way of saying, well, they'll say the dot represents Alice, and then draw every force as an arrow starting at the dot and then pointing away in the correct direction. So we would have, for instance, that the weight pulls down like this, and then that the rocket pushes up like that. I am not a fan of this method, to be honest, and I don't tend to use it. But I want to flag it that the committee has started being very explicit as to where they want forces attached. They always want them, it seems lately at least, attached to the dot and then pointing away from the dot, so that the arrowheads are always not in contact with the object you're talking about. I think they do that to focus on the center of mass idea, but I like to do it the other way because I think that, for instance, especially when drawing like frictions and normals, it makes sense to draw them where they're acting rather than some arbitrary place off to the side. But that's just a matter of dialect, and you should know what the committee wants, which is the one on the right. By the way, then we do the same problem, except now we're going to ask what is her acceleration, and we can just jump to see how that works out. Here we have the problem, we have her diagram, and then we have how to solve it. Well, we set up that F net equals ma, but we can see that the F net is Fr in the y hat plus Fg in the minus y hat, and then ma in the y hat. This is maybe a little excessive to bring in the unit vector notation, but it's the technically correct way to do it. On the other hand, there's a y hat in every term, so I can cancel it, and I do. And then we're left with Fr minus Fg equals ma, and then we can just grind out some numbers. I don't know, somewhere along the line, apparently, the number changed from earlier in the problem, but it doesn't change any analysis, and we get, for this one, 4.4 meters per second square. All right, a box is pushed along a rough floor using a stick as shown above. Draw a free body diagram for the box, and just as a reference, along a rough floor is a code word for include friction. There is some friction acting on the box. So again, in doing free body diagrams, how do you know when to stop? How do you know you have all the forces? And it's usually pretty easy. You end up starting off by drawing first the one for gravity. You say the object has a weight, because that's a not contact force. And then you draw a force for everything else in contact with the object. So for instance, there is a normal force, which is holding the box from going through the floor. And then there is a frictional force, which is resisting the motion of the box along the floor. And then finally, of course, there is some sort of push from our stick. I'm going to call that F sub P for push. And we should say that that actually tells us that Fn is probably a little bit less than Fg. I drew them equal, but I should probably take them out. Sorry, lied. It should be a little bit more, because if we think about the forces, if we go back to sort of the AP way of doing this, and they would say draw this, and you'd have some force like this. Did that at a bad angle, so let's try. Some FP like this, and some FG like this, and FN like this, and FF like that. Well, we see that FP has a downward component, so it and gravity will be pointing one direction, and FN is going to have to balance that, so it'll be larger going the other way. But again, free body diagrams are less about getting the magnitudes correctly than it is about indicating the forces and the directions they're in. Drawn a little bit more neatly, something like this. All right, here we have a little demo about how inertia works. It's not directly free body diagrams, but it's not terribly far off. We have a ball which is going to be suspended from one string and another string that hangs from it. And what happens when the string is tugged rapidly or when it's tugged slowly is what's going to go on here.
In this demonstration, I have two identical heavy balls hanging from two pieces of identical string. Below each ball is another length of string. Now with this first ball, I'm going to quickly pull down on the string. What will happen? Will the top string break, or will the bottom string break?
So give yourself a second to think about what would happen.
Let's find out. So as you can see, the bottom string broke. This is because the heavy ball has a lot of inertia and it doesn't want to move. When I pulled down quickly on the string, I didn't give the ball enough time to start moving. Now I will pull down on the second ball, but this time I will pull very slowly. The question is, which string will break first, the top string or the bottom string?
Again, give yourself a couple seconds to think about it, and then let's see what happens.
All right, so we pull slowly. The top string broke this time because I was able to slowly accelerate the ball, get it moving. I was able to pull the top string apart.
So, to be a little, well, spin this a little bit differently than he did at least. In the second case, or in all cases really, the top string has a tension which is equal to the weight of the ball and the weight of the strings, and of course any extra force put onto the top string. And likewise, the ball, of course, has to have forces holding it up. So if we sort of think about the free body diagram of the ball, here's the ball, and we have its own weight pulling it down, of course, but we also have a string holding it up here, which we may call FT1, and a string pulling it down, which we may call FT2. And in essence, what we're saying is if the string tension in the lower string is large, if we pull fast, which really means when we pull really hard on it, then the tension will be more than the object can move, because we have to accelerate the whole object downward, and to do that requires a certain amount of tension, and if the tension in the string is too large, then it will go before the ball can start moving. But if we pull gently with FT2, then it's just going to increase what FT1 has to be to hold in place, but eventually that will exceed what the upper string can handle, and so it will fail. So here the inertia of the ball matters because its tendency to not accelerate controls the size of the forces that are going to go into it. All right, final example. A tugboat is pushing two barges labeled 1 and 2 so that they speed up. The mass of the tugboat and barges and the acceleration systems are given in each case. Ignore the effects of fluid friction. That's both incredibly generous and incredibly important. That would make this problem a lot harder if we had to include that, but we don't, so yay for that. It says draw a blue circle around the cases where the force of the tug on boat 2 is greatest, and a red circle around the cases where it is least. So we look here and we say, well, what are the forces on boat 2? So let's draw, here's boat 2, And boat 2 is getting acted upon, of course, by boat 1. I'll call that F, just A. And boat 1 is getting a force which is FA the other way, plus the force from the tug. And we see, and this is the key bit, that the force of the tug is not applied to the force on boat 2. The tug is not in contact with boat 2, so it doesn't exert any forces on it directly. It has an effect via the intermediate one, but it's not directly exerting the force on 2. So this is sort of a trick question. They are all 0, which means they are all the greatest, because they're all the same, equal to the maximum, and they're all the least, because they're equal to the minimum.